The water cycle, or hydrological cycle as it is often called in scientific context, describes the continuous movement of water through the atmosphere, the soil, and the oceans. Water evaporates from the oceans, seas, lakes, and land, forms clouds, then falls to the ground as rain or snow, seeps down to reach underground aquifers, flows through rivers, and finally returns to the oceans. It is an ancient, powerful cycle, but also extremely delicate, sustaining both natural ecosystems and human activities. This complex exchange can be described quantitatively through the hydrological balance equation, which in its simplest form is P equals ET plus Q plus delta S, where P is precipitation, ET is evapotranspiration, which is the sum of evaporation, and transpiration from plants. Q is the runoff, that is the water that flows in rivers and through the soil and returns to the oceans. Delta S is the change in water storage within the system in aquifers, in the soil, and in reservoirs. This equation helps us understand how water moves, is distributed, and accumulates within a given watershed, or, on a larger scale, globally. Yet, in this description, a fundamental element is missing, one that radically influences the hydrological cycle: the human being. Since the very beginning, humans have learned to use water for their needs: drinking, irrigation, energy production, and building civilizations. To account for human impact, the hydrological balance equation can be extended by introducing a new term: anthropogenic water withdrawals, which we denote as W in our balance equation. These anthropogenic water withdrawals represent the water taken from the natural system for agricultural, industrial, and civil uses. The balance equation thus becomes P equals ET plus Q plus delta S plus W. In this formulation, the term W highlights how direct withdrawals alter the natural balance, changing the distribution of flows and reducing the amount of water available for ecosystems, for the recharge of water reserves, and for surface runoff. This quantitative approach is fundamental for planning a sustainable use of water resources, especially in contexts exposed to water stress and climate change. The concept of water security thus becomes central. This term refers to the ability to ensure that all people have access to a sufficient quantity of water that is of good quality and is provided in a sustainable and resilient manner, even in the face of population growth and economic transformations. If we analyze how water is used on a global scale, we see that agriculture is the main sector consuming water on our planet. In fact, on a global scale, 70% of freshwater withdrawals are used in the agricultural sector, 20% in the industrial sector, and 10% in domestic municipal use. This means that 70% of freshwater withdrawals are used to irrigate fields, and this irrigation water is essential for global food security. Why? All plants, including cultivated ones, absorb carbon dioxide from the atmosphere to carry out photosynthesis, and at the same time, they transpire water that is taken up from the soil. The process of photosynthesis requires carbon dioxide, solar energy, and water. It results in the production of glucose, a sugar, and the release of oxygen into the atmosphere. The exchange of gases between plants and the environment causes plants to lose water in the form of vapor through a hydrological process known as transpiration. This represents a significant water loss. In fact, about 95% of the water drawn up by the roots is used in the process of transpiration, while only around 5% is actually used in the process of photosynthesis itself. However, the water present in the soil, coming from the infiltration of precipitation, is not always sufficient to meet the water needs required for food production. This is why irrigation is used. Thanks to the AIDA model, which stands for Agricultural Irrigation Demand Analyzer, developed by our research group at the Politecnico di Milano, we are now able to quantify the net irrigation requirements of agriculture in a spatially distributed and dynamic way. In the case of Italy, these water requirements amount to about 10 billion cubic meters per year, which corresponds to approximately 50% of the country's total agricultural demand. That is, the sum of rainwater and irrigation water. On a global scale, irrigated areas account for about 20% of cultivated land, But even though they represent only about 20%, they provide as much as 40% of the food produced on our planet. Without water, it would not be possible to farm, raise livestock, or ensure food security. Water is therefore, in every respect, the first invisible ingredient of what ends up on our tables. However, the agricultural use of water presents enormous challenges. In many cases, in fact, irrigation is carried out inefficiently and unsustainably, with significant losses along the network and sometimes using outdated techniques. Water scarcity, which represents the failure to meet the demand for water resources, can be of two types: physical and economic. Physical water scarcity, a significant global challenge, occurs when there is simply not enough available water to adequately meet the essential requirements of both human populations and the delicate needs of ecosystems. This critical shortage can arise due to various natural causes, such as a profound lack of sufficient runoff, which is often directly caused by prolonged periods of exceptionally low precipitation levels. Economic water scarcity, on the other hand, occurs when water needs are not met even though water is available. In these cases, the cause can be attributed to the lack of hydraulic infrastructure, investments, or the capacity of institutions to manage the water resource in order to make it accessible to the population. Economic water scarcity is a typical problem in developing tropical countries with unstable economic and political systems. It should be emphasized, even though it may seem counterintuitive, that malnutrition is more often found in countries affected by economic water scarcity than in those affected by physical water scarcity. Although it is well known that water is essential for food production, situations of competition between different uses of the resource are often observed, resulting in water being used for irrigation in regions where water is already scarce, thereby worsening conditions of water stress. Competition for water resources arises where multiple sectors are heavily dependent on water. These sectors include not only agriculture, which we have already discussed, but also industry and the energy sector. Water is in fact crucial for cooling thermoelectric plants and for the production of hydroelectric energy, which globally accounts for about 15% of total electricity production and half of that from renewable sources. In context of increasing demand and limited availability, this competition among agricultural, civil, and energy uses for water resources makes the need for integrated and sustainable water management even more urgent. To address these challenges, integrated strategies are needed that take into account the interdependence between water, energy, and food, the so-called water-energy-food nexus. To this end, it is necessary to promote planning of agricultural and territorial development that protects natural water sources, takes greater account of the timing of the hydrological cycle and the geography of water, improves the efficiency of irrigation systems, and at the same time regulates their use. It is necessary to invest in water education and governance and, where needed, to promote innovative technologies aimed at producing non-conventional water resources. Only in this way can we ensure a future in which water remains not only a natural resource, but also a source of life, security, and prosperity for everyone.